Hello, today I'm going to be talking about bit shifting registers. Now, registers are a space in memory that hold individual binary values. And if we can find a way to move these binary values about, then they can be used to perform some useful operations. For example, if we want to multiply a binary number by 2, all we have to do is shift all the individual binary bits to the left. And similarly, to divide a binary number by 2, we shift all the binary digits to the right. Now, what we need to look on is a way to store those individual bits, and flip-flops are the most common way of doing that. In this video, I'm going to be using JK flip-flops rather than the D flip-flops. JK flip-flops are very simple and can be constructed using SR flip-flops. The table here show the truth table of the SR flip-flop is given on the right, and it does not work on this state. But to convert the SR flip-flop to a JK flip-flop, we just need to make two connections. One of these is this, and the other one is connecting the NOT of Q to this. And that will give us the JK flip-flop. Now, even within the JK flip-flop, we need only the values of two rows, these two. And what is particularly special about these two rows is that you'll notice that if J and K are opposite, the value stored in the flip-flop, which is Q, will be equal to the value of J. Now, building upon this theory that if we input opposite values of J and K to our JK flip-flop, then we can achieve storing the value of J within Q. So, if I were to draw JK flip-flops here, and connect them in series along with a clock, you can see how this can be used to store the memory. For example, initially, say the Q here is 0 and the Q here in the second flip-flop is also 0. If we pass the value of 1 to J and then turn the clock up a pulse, provide a pulse to the clock, then Q will be set to 1 in the first flip-flop, and therefore that makes the J in the second flip-flop equal to 1. And say we now pass 0 as an input, that will give us J as 0 in the first flip-flop, Q as 0 as its second state in the first flip-flop, and that 1 initially stored before in the second flip-flop in J will now go to Q. So the final value will be stored as 0, 1. Now it is important that J and K are always opposites of each other. So it would be useful to add a NOT gate at the beginning here. Seeing the shift right register, it's easy to determine how we can make the shift left register. And to make the shift left register, all we need to do is take the shift right register and flip it over by 180 degrees. And essentially what happens is that the input is provided from the right hand side, and which means that the bits will now be shifted towards the left. There is no fundamental difference in their structure. Another type of register is the shift around register, which means that any data value passed and say a shift right operation is sort of applied, then this least significant bit should become the most significant bit, or vice versa. The most significant bit should become and append to the end to become the least significant bit. Now, the way these two can be designed is these systems can be designed is if a shift say right register is taken and the output of the shift right register is connected back into the input of the shift right of the same shift right register. What this will do is make a loop for the last data value to pass from the rightmost position to the leftmost position, and similarly to make a similar register that does the opposite work. This is a shift left register, and its output can also be fed to the input to make it such that it is looped and the data values can be transferred. In a JK flip flop system, this can be shown like this, with the connections being very similar, except that the output Q of the last flip flop goes into the first J value of the first flip flop, and the not Q naught of the last flip flop goes into the K value of the first flip flop. The last type of shift register I'm going to be looking at is the bidirectional shift register. Now, the bidirectional shift register can act as a left shift register and a right shift register. And what that means is that it can function either way depending on the inputs we put in. The input that determines whether it works as a shift right register or a shift left register is this value right here. So, as an example, let's say that if this value is 1, then that means all these gates and gates are disabled and will sort of output 0. And the reason for that is because this is an AND gate, any one value is 0, the output is automatically 0. And for the gates on the left side, that will be equal to the shift right input provided here. And that means when this shift right input is provided to the first OR gate, then this value here will be shift right, the input we provided, and that means that Q, this will be Q as the output, and Q will be the input going into J. And as we can see that this works perfectly as a shift right register. And on the other hand, if this value here, the controller bit, was 0, then that would disable all the gates on the left hand side of the OR gate, which is these gates, and that would mean that this would work as a shift left register. Now, the position of these two AND gates and the one OR gate matters because it is between and before and after each flip flop. So it is used to determine which direction the bit should be flowing, and so that it can determine which way to work, as a shift left register or as a shift right register. I am going to be showing you some working of these registers on logism, because that is the best way we can understand it. Now, these shift registers only work if we have a clock pulse present. So let's say, for example, that we input 1, the input is 1, J is 1, K is 0 in the first flip flop. On a clock pulse, it would mean that the Q of the first flip flop right here will be equal to the J value, which is 1. Perfect. And that would mean that the J value of the next flip flop will be 1. And if we pass in the input, say 0, and then provide a pulse, that means that the J value is 0. The pulse made the Q value of the first flip flop 0, and that in turn made the J value of the second flip flop 0, and the Q value 1 because of the previously stored J value of 1 within the flip flop. If we look at the shift left register, that works in a very similar way also. I explained before, it's just 100-degree mirror. It's a mirror image of the shift right register. The shift around register is basically the output connected back into the input and Q naught going back to the K part of the JK flip flop. Finally, looking at the working of the bidirectional shift register here, we can make it work as a shift right register like this, and if we move this data bit to be 0, then we can input 1, as you can see the value 1 from the right hand side, which makes it a shift left register.